The other thing I wanted to talk about were these. We're going to do this a lot in lab. We'll do it a little bit in class too. But when we talk about our motion, we often plot position. I'll just do x. Position versus time. Velocity versus time. And acceleration versus time. And so sometimes, let's say we're just throwing something up into the air. Okay, give it an initial speed straight up. It goes up to its highest point, stops, starts coming back down, and then I catch it. So what would that look like? The position, I guess I could have made that a y instead of an x, but the position as it goes up would look something like this. There, let me. It's hard to draw a parabola. Close enough. Okay. Looks something like that. It's a parabola. Velocity starts out, what is it going to start out at? Big positive number, right? Because it's the slope over here. The slope right there gives us the velocity. That's a big positive number, the slope right there. When it gets to its peak, the slope is 0, and over here, it's a big negative number, right? Okay, so it starts out, big positive number. At the peak here, it has to be 0, and it ends up over there. So it's going to look something like this. All right? And the acceleration is the slope of this curve at any given point. So that means the acceleration is constant. It's going to be minus 9.8, right? So we just talked about slope. So when you're going down, when you're going in this direction, the slope of the curve above gives the velocity at that instant. The slope of v versus t gives acceleration at that instant. Okay, so you see how you're going down from position to velocity to acceleration. You can look at the slope, and that helps you fill these curves out. But you can go up also. The area under A versus t gives the change in velocity over that period. The area under V versus t gives the displacement for that time period. So should we see sort of what we get here for, if we started out, if we toss this thing at 30 meters per second, And our time was 3, this is going to be 3 seconds, right? So we give it a toss 30 meters per second. We know the acceleration, we're going to use 10 meters per second squared as the acceleration of gravity. So after 3 seconds, it comes to rest momentarily. Then it's going to start coming back down. And 3 seconds later, I catch it again. Okay? So what's the area under the curve for this first part here? I want to know how far did it go up. So the area here is, what is that? 1/2 base times height, right? 30 times 3, 45. And what is that? That's meters per second multiplied by seconds. So that's meters. What do we get for the area from 3 to 6? Negative 45, because that's below the x-axis. The t-axis, I guess I should say, right? Below the time axis, the horizontal axis. If it's below the horizontal axis, it's negative area. So in the first case, delta x was positive 45. It started at 0, ended up at 45. In the second case, delta x was negative 45. It started at 45, went back to 0. And from the beginning to the end, delta x was 0, right? It started in my hand when I let go, and it ended back in my hand. So there was one of the problems that a lot of you had trouble with dealt with this. They gave you velocity versus time, and they asked you to rank the displacements, right, over different time intervals. So you needed to look at the area under those curves, add them all up. Some were positive, some were negative, some were 0. Add them up, and that's the displacement for that time interval.